Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be going adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Thank you. Now we'll be changing our discussion a bit. We'll talk about another very important aspect of modern physics. You see, if you look at the design of your course, you have to learn two types of optics. One is called classical optics, where you learn optical phenomena like interference, diffraction, etc. And is modern optics, which includes laser and fiber optics. So now today, I'll begin with lasers. So first and foremost question comes in, obviously, what is laser? You see, by this time, almost everybody of you have heard about the particular term laser. Okay, but what does it mean by laser? How do you produce laser? What is the basic necessity of production of laser? How laser is different from ordinary light? Where we apply laser? What are the variety of lasers that you can produce? And because depending on the variety and the quality of lasers, the area of application is also changed. Okay, so all these things we'll try to know, because these lasers have got a profound application, particularly to the students having, for example, for mechanical and civil engineering people. You'll be doing the welding that you do in workshop. Now you have got laser welding. The biomedical student, okay, you'll be doing now laser for retina operation, retina surgery. For years now, lasers are used. So it's bit in this course, actually we try to, the main objective of this course is actually try to develop what is the basic concepts of what is laser, how do you produce it, where you apply it. Later on, actually, for some of the chapters, because in second year it's still specific, you can actually learn this thing in more detail depending on the area of application. Now in the, this is the, so therefore in terms of laser, this is our class 1, okay, 16 in a row. So in this first class, the major of lasers, the major objective is to introduce you with the term laser and what is laser, how it is produced. Okay, or we'll use a term, actually phrase called lasing action. So today I'll try to introduce with that. So it is expected after attending the class you'll be able to explain how laser is produced. Okay. After that, we'll get into more details, possibly in the next video lecture. So let me get into this details. So this is me again. Now come to the case of definition of lasers. Okay, basic definition of laser, as all of you can see, laser is an abbreviated term. It stands for light amplification by stimulated emission of radiation. You see, so many variety of very different terms are used. The light means it is, I'm talking about visible radiation, visible light. There is our optical spectrum starting from red to violet, okay, or violet to red, whatever you say. Amplification, okay, in basic electronics we are learning transistors. Amplification means in transistor what you amplify, the applied initial input voltage. So here also you can amplify the do some sort of amplification. Who will be amplified? Light will be amplified. Or if you think in terms of photons, number of photons will be increased. So we need some special mechanism for that. I want to increase the number of photons. Okay, I want to produce more lights. But how do you produce that light? You see that what I have kept so many question marks there. The method is stimulated emission. Okay. Now, the concept of stimulated emission was coined by Albert Einstein in 1917, okay, long back, okay, and it is applied in case of lasers. Initial device was measures. It was done with microwaves on the frequency range varies. These are all, the word radiation is important. These are all electromagnetic waves. Visible spectrum, so wavelength is like 10 to the power 14 hertz, and microwave is like 10 to the power 9 hertz. Okay, initially measure was produced using this principle of stimulated emission. Light means that measure or electromagnetic radiation was amplified, but when you do it for visible light, it becomes laser. So laser is an abbreviated term. Laser stands for amplification of light wave. Light wave means it's a visible spectrum, but in general it is a part of our electromagnetic spectrum, you know. So in order to amplify light, you have to do something. What is that something? Something is that question mark. That is the process of stimulated emission. So I repeat it, laser stands for an abbreviation. An abbreviation is coming because of the way you are amplifying the light waves, visible light, okay, and that is the stimulated emission. So that means, you see, if you look at all the 4 terms I have written there, I don't have to introduce you with radiation, electromagnetic wave, which I have already done. Okay, it's a simultaneous vibration of electric and magnetic field. Okay, I don't have to introduce you with the word visible light because that is a part of the electromagnetic wave, the optical region. And I also don't have to introduce you with the term amplification because you already introduced with the amplification. In any case, everybody knows, okay, that is increase in something, enhancement of something. Okay, in this case, enhancements of light, photons. So what is most uncanny term there is the term in violet there, that is a stimulated emission. So before explaining that how you produce laser, or what is the basic action of lasers, operation of lasers, or popularly called lasing action, okay, I'll first tell you what is stimulated emission, because that is something unknown and uncanny to you. Okay, so let me introduce you that. You see, there's a bit of history here, the history of lasers. As you can see, it was invented in 1958, okay, by Charles Townes. Okay, he's got the Physics Nobel Prize, okay, in 1964. It's a Nobel Prize winning concept, okay, and Arthur's Shallow, okay, of Bell Laboratories. They invented the lasers, okay, and as I mentioned, it was invented by, in the case of microwave initially, and this is the original paper. In 1958, this paper was published. So it has got a history, okay? You can see there. So initially it was called measured in 1958. Microwave was amplified, but the basic principle is same. You amplify some electromagnetic wave. And as I mentioned at the beginning, now laser means you do it for visible light, okay? And it was actually originally for visible light, it was done in 1960. Now, these are some of the qualities or attributes of lasers. Laser is highly monochromatic. I will explain every term how it comes. Okay, highly monochromatic means your wavelength is almost fixed. Please see, be careful. I'm using the word almost fixed wavelength because in my last topic was the Heisenberg's uncertainty principle. There I told you, could not be absolute monochromaticness because there will be some line with broadening because of the uncertainty principle. So it is almost nearly monochromatic radiation you are producing. Laser is highly coherent. Coherent means all the light wave moves in the same space. Okay, there is no phase difference between them. It is highly polarized. Okay, so the plane of vibration of electric field, okay, are all same. In one plane they vibrate. Highly directional. Okay, even after 2 kilometers it can move. Okay, without any divergence. Okay, and highly intense, obviously, because many photons, you're amplifying photons, okay, can focus over a small area of 10 to the power -6 meter even, okay. So basically these are attributes of laser. So this is the concept of monochromaticity, you see. But normal lights are all polychromatic light. It makes a mixture of so many colors, okay, red to violet you can see. But you can see here, it's a beautiful picture, okay. Try to realize, you see how wavelength is changing from violet to red, okay. As you move from blue to red, you see wavelength is increasing in a scale I have shown there. But laser is absolutely monochromatic. For say, these are some of the examples of the production of sources of laser. Helium neon source, I will discuss them in detail. Okay, there only the this delta lambda is a lack of monochromaticity, or it is called line width broadening of the laser. Okay, you can see this is delta lambda. Okay, just to mark it, this is delta lambda. Okay, there is a loss of monochromaticity by this much. It is very low, only 0.2 nanometer for helium neon laser, and for dart laser it is a bit more. So with helium neon you get more monochromatic light. You can see 6325 angstrom that you are seeing there, that corresponds to red light. Okay, helium neon laser and diode laser both are in your syllabus. I will discuss them, don't worry. So I'm just giving this example to give you an idea of the nature of monochromaticity. Okay, it is a highly almost monochromatic, only 2 angstrom, 0.2 nanometer means actually 2 angstrom deviation. Okay. Now, another very important concept is directionality. You see the picture, the left-hand side picture is a usual normal conventional source of light where the light is moving in all possible direction. So there is no defined direction, but laser is highly directional. Okay, the beam divergence is calculated there. There are some standard practicals also, you can calculate it. Okay, it is equal to beta lambda d by d, where d is the beta is 1. Okay, for amplitude distribution, lambda is the wavelength and d is the beam diameter. Okay, there is a beam divergence. Actually, it's very almost divergence is very less. Okay, even for a very long distance. Laser is highly coherent, as you can see. There is an incoherent source of light. You please see, you realize in the picture how incoherent the ordinary light can be. Okay, red, blue, green, magenta, okay, greenish blue, violet, orange, everybody is there. Okay, their phase are not same. Okay, you can see there. Okay, if I draw a line here, any arbitrary line, okay, they are not in the same phase. Okay, if you look, if I draw a line here, you see they are in variety of phases. This is at minimum, this is slightly above, this is at negative, negative, this is at 0, this is almost in the same phase, the first and last one. So they're not in the same phase. But come here, you look here, there is already a red line. They are absolutely in the same phase, highly coherent. Okay. Coherence means you have to maintain a wavelength should be fixed. That is you see how do you realize wavelength is same? Here there are so many colors, so lambdas are different. The two conditions are there for coherence. First, wavelength should be same, and the phase difference should be constant. Okay, you can see that there is no phase. They will move with constant phase difference, or there is no phase difference in my picture, as you could see. Okay, so laser is highly monochromatic, highly directional, highly coherent. Okay, these are all the good news for the lasers. Okay, now these are some more okay, so these are attributes of laser. So if these are laser is highly monochromatic, highly directional, highly you see the beam divergence is very low. Okay, that's why the directionality is very high. So and highly coherent also, as you can see in the last picture. Now these are some of the comparison with the ordinary light. You can understand the key is these three lines. The ordinary light source may be coherent, maybe in general incoherent, but laser has to be coherent. All of them will be in same wavelength, same phase. And intensity of the ordinary light is it's all distributed amongst the various lambdas because of polychromatic nature. And you see, if you look at the picture there, the second picture I am talking about, you realize, okay, here this is absolutely monochromatic. This is lambda plot, so lambda is almost fixed. Slight divergence is there, almost fixed. Okay, lambda is almost fixed, but here lambda is not fixed. It is polychromatic. There are so many colors are mixed here. Okay, with ordinary light. So laser gives you absolutely monochromatic light, highly monochromatic light, I should say. And normal lasers, you see, this highly directional. It is maintaining the same direction. Okay, it is maintaining the same direction. Okay, sorry, highly directional. Okay, so there will be no divergence. Divergence should not be there, but normal light sources are usually divergent. Okay, so you can see it. It is so profound. Okay, this has got so much of good qualities. Okay, some more cases. Okay, you can see the normal source is moving in all directions, but laser highly directional, and you see the level of divergence. Okay, Normal lasers up even after up to 2 kilometers there is no divergence. Okay, with lasers. Now, automatic question comes in. So I've introduced all of you with the term laser. Okay, what is laser? And there we have identified a keyword called stimulated emission. Now I'll try to realize what is stimulated emission. And you can realize by this time that I have attribute is described what is the speciality of laser, why it is so special, highly coherent, highly monochromatic, highly directional. And I compared with ordinary light also, which puts laser in a very good platform now. Okay, you can realize it is such a important radiation. Okay, so now automatic question comes in, that how do you produce laser? The answer is that by stimulated emission. To answer this question, I will now address various types of absorption and emission processes. Some of the some of the ideas you already know, but stimulated emission is unique. Okay, because it was coined by Einstein in 1917, and which is utilized here. So one by one, I will develop that idea. For that purpose, I request you to look at the picture there. You see, a very beautiful picture is there. Okay, you see, you can see the radiation there. You can see the radiation. You can see the picture there. Look at the picture. Okay. You see, we have chosen aluminium as an example. Okay. We have chosen aluminium as an example. Just a second. Okay, let me keep the animation on. You see, if you look at the picture, you see this is a nucleus and electron orbitals are there. All these things you can see. Aluminium has got 13 atomic number. They are distributed like that. 13 proton, 14 neutron. So it's a beautiful picture, na? And you see, if you try to realize those energy levels, and nucleus is at the center, and these are variety of energy levels. All of you have studied Bohr's theory sometime in your life. So E1 is like ground state, lowest energy state, and E3, E4, E2 all are higher than, having more energy than E1. They are called excited state. And more you go up, you lose your stability. Okay, they are okay. Understand? So E1 is the ground state. Now look at the picture. You see the same thing I told you. More you go up, you lose your stability. So if you are living at E1, ground state is always stable. Actually, electron can stay in the ground state for infinite time if you do not excite it. Okay, and the amount of time electron can stay in an energy level is called its lifetime. So in a ground state is infinite. But bad news is that in those excited states, you see, nature does not permit anybody with higher potential energy. So the moment electron is in E2, it's in the E2 energy level, its energy will be equal to E2. Okay, E3, E4 like that. More it moves energetically up in the higher and higher, these are called Bohr orbitals, you know. Okay, electronic energy will increase, and nature wants stability. So the lifetime of the electron, so nature wants electron should not stay there for in the high energy state for a long time. So it loses stability. So ultimately results in a very small lifetime, short lifetime in the high energy states. So if you plot it, you see it is like this much. Okay, various energy levels are there. In the ground state, the lifetime is very high, infinite. And high energy states, as I mentioned there in the picture, like R2, R3, R4, whatever you see lifetime is much smaller. Okay, 10 to the power minus 9 seconds. Okay, very small. So I put like steps there. Okay, so if you are living at the top, it's not safe. So go down. That is a message of nature. So that's why it is always, you see, nature wants everybody should be in the lowest of energy state. That's why the river come from the top of the mountain to the sea. You see, it is always easy to get down from the top floor of a building. If you have to get up in the top floor of a building, it is difficult because you have to gather energy. Okay, but nature do not want that you should be at the top. Nature wants that it should be at the lowest of the energy level. So very easily you can lose energy and come down. Okay, so that is a nature answer. That's why the lifetime of the electron for electrons also, it wants that they will be in the ground state. But so in the excited state, if you put it, it will be soon come down, and that soon is too soon. You see, lifetime is 10 to the power minus 9 seconds. Now this process of that electron cannot stay in the excited state, it has to come down. What does it result? If it is coming from say R4 to R3 or to R2 or whatever, wherever it may be, it is losing energy. And if it loses energy, because of Einstein's formula, loss of energy is equal to hc by lambda. That means it is losing radiation. Now, this is in this natural process that somebody electron coming from high energy state to low energy state and losing radiation is called spontaneous emission, okay, which we'll discuss. And it is a usual emission process that takes place in nature. We'll discuss that. But before that, another wonderful information you see. If you look at the picture, I kept two pictures there, okay. One is the left hand side picture is the, suppose electron is, I have got electron is in the ground state, if or the lowest energy level. So if electron is in lowest energy level, we say atom is in ground state. Suppose instead of one atom, I have got 100 atoms. Okay, if in 100 atoms, suppose in all 100, electron is in the ground, in the lowest energy level, the atom is in, all the atoms are in ground state, which nature wants, but may not be the story. It might happen in some of the atoms, electron is in the high energy state. If electron in any one of the high energy state other than ground state, any energy state other than the lowest energy state, okay, then what would happen? We say atom is in excited state. So if electron is the lowest energy level, lowest of the energy levels, the atom is in ground state. And if electron in any one of the high energy level, we say the atom is in excited state. So because suppose I have got a container full of hydrogen atoms, nature wants all hydrogen atoms should be in ground state, but it may not be the story. Suppose out of 100 hydrogen atoms, suppose for example, considering 100, okay, suppose out of 100 hydrogen atoms, suppose in 90 of them electron may be in ground state, and remaining 10 it may be in high energy state. So in those 90 atoms are in ground state, and the remaining 10 where electron is in the high energy state, they are in the atoms are in the excited state. So try to realize the moment I am moving from electron's residence to the atomic description. If electron is in the lower energy level, atom is in the lowest energy state, ground state. If electron in an atom is in high energy level, atom is in excited state. And nature do not want that, okay? It does not want that anybody, any system would be in its excited condition. Now, another important concept, as I mentioned, suppose I have got a container full of hydrogen atoms. I just show you. Suppose I've got a container. Okay. It is full of atoms, full of hydrogen atoms. These are hydrogen atoms. And suppose there are 100 such hydrogen atoms are there. What is expected, what nature wants? Majority of the atoms should be here in the lowest energy level. Okay. Majority of the atoms should be here. Okay, this is the ground state. Majority of the atoms should be in the ground state. And only one of them, say, suppose here in the picture, I presented 6 atoms. Suppose one of them is only in the ground state, and obviously this is one of the excited state. Only one of them is an excited state. Now this is the law of nature. Most of them should be in the ground state. Out of 6, only 1 is in the excited state. So that means only 16% is in the excited state, and remaining close to 84% is in the ground state. That is the law of nature. Most of the atoms are in the ground state. Okay. But if the opposite story happens, that is against what nature wants, that is the opposite story you can see. This is the excited state. What does it show? Out of the 6 atoms, again, only 1 is in ground state, and remaining are in the excited state. If this is happening, then you are actually violating the usual condition. Okay, this is called population inversion. But most of our natural system is normal population. Majority of the atoms in a system of atoms will be in ground state. But population inversion is a term I'm just introducing in front of you because for laser it is a very important term. If most of the atoms are in the higher energy state, then your population inversion, that means whatever is usual, that is not happening, it is inverted. That is called population inversion. Okay. So the idea is that it might happen if you choose a system of atoms. Some of the uh, atom electron may be in lowest energy state, the atom is in ground state. It is expected for most of the atoms. And if electron is in the high energy state, your atom is in the excited state. Okay, that is the point. Again, the same picture I am showing. Okay. So I hope I have illustrated the basic issues to you. What are the atomic system, where the electron should be, low energy level, high energy level, concept of ground state, concept of excited state, normal population, and the population inversion. Okay, now come to this picture. You see, there is a small calculation I have made here. This is giving an idea about the mathematical description of the normal population. Okay, now population can be, you see, there is a famous Boltzmann equation, okay, which tells us if there are two energy levels for you to understand. Suppose I have got an atomic system. Suppose these are the two energy levels. In E1, number of particles should be suppose N1, and this is another energy level, E2. Number of particles is N2. Number of particles in an energy level, E1 is given by this formula, and in N2 is given by this much. So that the ratio, the relative population is that much. N2 by N1 is equal to exponential E2 minus E1 by KT. So what does it tell you? It tells you that N2 is equal to N1 exponential minus of delta E by KT. Okay. So what does it imply? It implies at low temperature, what would happen? Low temperature means you have to make, if you apply limiting conditions, say T goes to 0, okay, to the power 0 kind of thing. So all the atoms should be in ground state. N1, N2 will be equal to N1. Okay. What would happen? At low temperature, I mean T goes to 0. So it is like e to the power exponential some constant by 0. So that means e to the power minus infinity type of quantity. So now at low temperature, that's why N2 goes to 0. And relatively higher temperature, what will happen? So T is high. Okay. T is non-zero. So obviously, you see there is a N2 is an exponential drop, but this is non-zero. Okay, that is a very important issue. Okay, but the number of N2 will be less. Okay, compared to N1. In a material at thermal equilibrium, atoms are in low energy state. You can see, and the high energy state, as I mentioned. And these are the limiting case. If T goes to infinity, which is absolutely meaningless, and E2 minus E1, that means energy levels are very closer together, they equal. But in general, N2 is lesser than N1. Okay, you can see there from the previous picture. Okay, N2 by N1 will be equal to exponential minus. So obviously, the number N2 will be lesser than N1. Okay, you can see there because N2 is equal to N1 exponential minus of something. Okay, so there is a decay compared to the N1 number. Okay. So this is normal population. More particles are in the grounds, low energy state. Now, what nature wants, let us visit. What nature wants, you see, three things can happen. First, absorption of radiation. You see, this is low energy state. Suppose this is E1 and this is E2. So what would happen? Suppose this is E2. You have made external radiation photon incident. So radiation is coming in. That means you are providing some energy h nu. So this electron attached here, electron is in the low energy level in a particular atom, will absorb that energy, will move up. So what electron is doing? It is absorbing the energy. If the energy is sufficient or equal to the gap between E1 and E2, it will move up. So this process is called absorption of radiation. Absorption means your electron is absorbing external energy and moving up. Next process is stimulated emission. As I mentioned, in this high energy state, electron cannot stay for a longer time. Okay, it cannot stay for a very long time. You see the picture. Electron is moving up. I repeat the story. These are the energy levels. So this is your electron. So it has to move up. Okay. Now in the excited state, lifetime is very low. So now it has to come down. Okay. Now come down means this process you try to realize. You see again, these are energy levels. Now it has to come down from the high energy. Look at the smiley there on the right. It has to come down from the high energy level to the low energy level. So if it loses energy, that will be coming as electromagnetic radiation. Now this is happening spontaneously because in the high energy state, lifetime is very low. The lifetime is very low, of the order of 10 to the power minus 9 seconds. So because of the natural process, nature does not want to disrupt it. Okay, within 10 to the power minus 9 seconds, okay, it will come down to the low energy state. Okay, and that loss of energy, because it is losing a bit of energy, you can see initial energy was E2. Now it is coming down to the energy state E1. This loss of energy E2 minus E1 will be equal to the HD. Okay. Now this is happening because of the natural process by the default as permitted by the nature. So this is called stimulated emission. You can see in the left hand side picture. So now, so absorption means absorption of radiation, as you can see there. This is the absorption of radiation. Okay. Photons coming in and it is moving up. And emission means emission of radiation. Emission is spontaneous here because of the low lifetime. Now we come to another process that is called stimulated emission. You see, emission will be there, but it will be stimulated. So what would happen? Some electron maybe in the excited state, but now you need an external photon for the bulk. If the photonic energy is equal to delta E, the energy gap between E2 minus E1, so what it will do, it will actually ignite, or it will ask one electron from the high energy level to come to the low energy level. Only because of the presence of this external radiation, and if its energy is equal to the gap between the two levels, one photon will come down. Okay, sorry, one electron will come down. If electron comes down, you see electron losing again this delta amount of energy. So what will happen? Because it is losing delta E amount of energy, so ultimately that loss of energy will be coming as a photon. Now what will happen? You see the external photon, because of its presence, has ignited electrons to come from high energy state to low energy state. It is not being absorbed. In absorption of radiation, the photon was absorbed by electron, electron was moving up by taking up the energy. It is not happening here. Because external radiation is present, so that is why the electron is coming down from high energy level to low energy level. This was predicted by Einstein. It is not, so it is there in the system. So now, because the electron is coming from high energy to low energy state, you get one more photon. So ultimately, you started with one photon that will be coming because of this from a different, maybe from a previous spontaneous emission. But that emitted photon, because of its presence, it is igniting another electron to come down from higher to low energy levels. So now you have got 1 plus 1, 2 photons. So this is the process. You see what we are doing, you are amplifying light. It has become 1 to 2. From 2 to 4, these two can ignite the emission of 2 more electrons from high energy level to low energy level, 2 to 4. 4 to 8, 8 to 16. Those are 16 will make 16 more electrons to come down from, because in an atomic system there are so many energy levels. So we get a lot of electrons, an avalanche of electrons will come out. Okay, please see the picture. It is moving up. Okay, now it is moving down, emitting one photon by spontaneous emission. Now what it would do? Okay, it will now make this to come down. So 1 plus 1, 2. So basically you can see, okay, moving up. So like this, these two will ignite 2 more photons to come out, and this process will go on and on and on. You see, these lines are very important. 2 to 1 to, oh, this is 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32, 32 to 64, 64 to 128, 122 to 256, 256 to 512, 512 to 1024. This is a huge growth will take place within seconds. The avalanche of electrons will be produced. So what you are amplifying? You are amplifying photons. So within a fraction of seconds, large number of photons will come out. So this is amplification of light. You are amplifying light by the method of stimulated emission, because this external presence of external photon is igniting the electrons to come from high energy to low energy level. So that's why one photon is making it 2. These 2 will make 2 more electrons to come down. So 2 will make it 4, and so on, as I mentioned. So within a very short span of time, a lot of photons, you get avalanche of photons coming out. So there's a huge growth in the photon number. So who is amplifying? Photon is a piece of light. Light is amplified. Okay. So this is the light amplification process. Now this is used in laser method. Okay. Huge growth of light photons takes place. Okay. So this is the basic process. That's why it is called light amplification by stimulated emission. Light is amplified. You see, 1 to 2 to 4 to 8 to 16, 32, 8 to 16 to 32, as we have written here, 64, 128. It will be growing. By which process? Because of stimulated emission. That's why the term is there. Light amplification by stimulated emission. Because stimulated emission is igniting the process of growth of the number of photons. Photons increasing means light is growing. Intensity is growing. So these are all now remaining processes will come up. All the photons will move together. So they are in the same phase. All of the photons will move in the same direction. They will maintain same direction. All of them are having same wavelengths, frequency. So they are highly monochromatic. So this is the way, this idea is utilized for the production of lasers. So it's a wonderful idea. Okay, what Einstein has coined. Okay. So now we'll actually, so we can understand therefore that this is a process by which actually we can increase the number of photons to a great extent. Okay. So we'll utilize, this is implemented in laser, but how do you actually produce a laser? Okay. Because you need common sense. This process to sustain, you need lot of electrons should be there in the high energy state, but which nature does not want. Nature wants lesser electrons should be in the high energy state. Okay. So what nature wants and what you need are differing, because you need more electrons should be in the high energy state for a long time. So nature allows normal population, and you need inverted population. More electrons should be in the high energy state. Otherwise, this cannot take place. So how we can achieve that? That needs a bit of calculation. Okay, Einstein did a bit of mathematics. Okay, so those things we'll learn, but not now. In the next video lecture, I'm presenting that. Okay, I hope you have got the message. What is the stimulated emission and how light is amplified? Thank you.